x between minus a third and a third. Okay, so now the question is, does it make sense if we plug in a third and minus a third into this series? Would it still be meaningful to do so? So to start with, let's look at minus a third first. All right, so we're going to put minus 1/3 into this infinite sum and see what it would get. All right, so we have minus 3 to the n, and then we're going to put minus a third to the power n. For x, this is your x, remember? And divided by n plus 1. And go from 0 to infinity. Okay, so the two negative sign is going to cancel, so we're going to left with just 1 in the numerator, and then the denominator is going to be n plus 1. N goes from 0 to infinity, so this is a series of the form of 1 plus 1 over root 2 plus 1 over root 3 plus 1 over root 4, etc. And the integral test implies f at minus a third with this series is going to diverge. And so therefore, this is not good. If you put in minus a third, it would not be meaningful. All right, so this 1/3 has to be removed. All right, let's look at the other endpoints. So we plug this 1/3 into the series as before. For x is 1/3, same denominator, 0 to infinity. So in this case, the 3 would still be cancelled out because, as you see, this is the same power n, so the 3 is going to cancel. But not the negative sign this time. So we would have minus 1 to the power n left on top, divided by n plus 1, n goes from 0 to infinity. So if we write it out as an infinite series, it's going to start with when n equal to 1, so it's still 1, 0 is still 1. When n equals to 1, I got negative. And this would be root 2, and then plus 1 over root 3 plus, when n is equal to 0, 1, 2, 3, so this is 3, that's negative, and you will have root 4. And then the next term is going to be plus, etc. So when you look at this, and you think of this is now the an, which is like 1 over root n plus 1, I should have said that is a negative sign as well. Then as you can see, the alternate series test is going to assert that this series actually converges. All right, so if you look at this term, so without a doubt this is a decreasing series, and it actually decreases to 0. And then you have this plus and minus sign in front, and so the alternating series test would assert it is converging. So in this case, if we go back to this interval, we will see that this point is actually good. So 1/3 is good, minus a third is not good. So therefore the interval of convergence for this example is different from the last few examples, that you could actually have from, except for minus a third, all the way to 1/3. Minus third is not included, but 1/3 is included. And the radius of convergence, however, is still the same as before. It's still 1/3. So in this case, the endpoint makes a difference. One is good, the other one is not good. So that's an interesting example. So let's look at one more example, then we would finish this section. So the next example we're going to look at is n times x plus 2 to the power n and divided by 3n plus 1, n goes from 0 to infinity. So the coefficients in this case is n over 3n plus 1. Now I will leave you to check that the ratio test would be n plus 1, x plus 2, n plus 1 divided by 3n plus 1, which is plus 2, and divided by n x plus 2 to the power n and divided by 3n plus 1. So if you look at this, and you simplify that, you will see this is what you would get. And when n goes to infinity, this is going to tend to x plus 2 over 3 as n goes to infinity. And what do we want is that we want to show that it is less than 1 if it is going to converge. And that you can solve by multiplying both sides by 3, so you get that. Or which is equivalent to having x plus 2 between minus 3 and 3, or you're going to have add minus 2, you get to have minus 5, and all the way to 1, right? So then we see immediately the interval of convergence, at least, is going to include minus 5, and that would be 0, and that would be 1. So then it would be every point between minus 5 and 1. So this is going to be the interval convergence, but the endpoint is a different story. So we need to check this one by one. So if we plug in, so the endpoints, you will have 1 first. So now we will plug into the power series. Remember, the coefficient is n, and then the x is going to be 1 plus 2 this time to the power n, and divided by 3 to the n plus 1. And now let's simplify this a little. So n goes from 1 to infinity. Yes, I think I should have 1 to infinity. So this is going to be 3 to the power n, and divided by 3 to the n plus 1. And so that translates to n over 3, 1 to infinity, 1 to infinity. Well, you don't have to do anything to tell that this is going to diverge, because as you can see, you can take 1/3 out. So actually you're summing up the n, so it's going to diverge like crazy. So this obviously diverges. Okay, so one of the endpoint is gone, so this point is not good. So the point at 1 is not good. We're going to remove that. It's a big hole there. All right, for the other endpoint, that is minus 5. We plug in, so we have n into minus 5 plus 2 to the power n, and divided by 3 to the n plus 1, 1 to infinity. So in this case, we're going to have minus 3 to the power n, and divided by 3n plus 1. So this can be simplified. The 3 is going to cancel, but you would have minus 1 to the power n times n, and then divided by 3, which translate to the following form. So when n equals to 1, this is going to be minus 1/3. And okay, so maybe here is another way to make it simpler. So I would, let's take 1/3. Let's take 1/3 out. which may be easier. So you would have simply -1 plus 2 minus 3 plus 4, etc. Well, I mean, this series cannot possibly converge because the individual coefficient doesn't go to 0. And so therefore this one diverges. So in this case, the series also does not converge at the other endpoint -5. So when we come back to this picture, we need to delete this point. So in this case, the interval of convergence would be from -5 all the way to 1, and the endpoint are excluded. Okay, so that's today's material. We look at power series, and we show that for power series, it has a region within which all x that you substitute, the series will converge, and that is called the interval of convergence. And then the length, half of the length of the interval is going to be called radius of convergence. And also then the endpoints are not known. You need to look at the endpoints by actually investigating the infinite series, whether it converges or not. And so basically that is today's material. And before we end, I would like to comment on the terminology of why it is called radius of convergence. So let's say this is A, and you would have A minus R and A plus R. Actually, in 19th century, mathematicians already know there is actually a circle around which, within which the series will converge. By that I mean that if I plug in a point xy and think of x and y is a complex number z, then every such point you pick within this radius, the series will converge. And in particular, when you choose the series, when you choose the point to be on the real axis, and that is going to coincide of exactly what we discussed today. But in fact, if you move up from the real numbers to even complex number up here or down below, as long as it is within this circle, then the power series will converge as a complex power series. And if you restrict only on the real axis, then it becomes real only, provided all the coefficients are real. So that's why there's this radius convergence came. And so the interval of convergence is in fact the whole circle of convergence. And so if you know where the center of this circle is, namely in this case is A, and I tell you the radius, then you automatically know that the power series will actually converge in this whole circle, center A of a given radius. But in the recent decades, people gave up the complex argument, and this is actually a big mistake, that we are actually becoming 200 years earlier as far as our knowledge is concerned, and that's going backward, not going forward, not advanced. Okay, so today this is all I want to say, and then the next time we're going to continue about manipulation of power series, and then we'll have more examples, and I will also show you some practice exercise in the classwork. Thank you very much for your attention, and let me know if you have any comments in terms of presentation. Thank you.